Okay, so as I said, we will now look at the experimental setup. So you can see here, ooh, it's our little photocell. Now, one thing I didn't tell you is that this power supply here, I'm going to draw an arrow here. Look, means what does the arrow mean? Normally in circuit, it means that this is a variable DC supply. We want to be able to change the value of V from positive to negative. Okay, so what does this mean? If let's say this is positive reading, it means that the anode is positively charged. If it's negative, then the anode is negatively charged. Okay, so I'm going to put all of this inside a single graph for you. Lego, scroll, 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 scroll. Alright, so now I'm going to plot out the graph. As I was saying, we are going to observe the ammeter reading. Okay, let me adjust thickness of my pen a bit. I'm going to observe the ammeter reading I. Maybe this is in microampere. Pretty small, can be even picoampere. Okay, and this one would be the potential difference. Alright, so just so you know, 0 is here, and I'm going to help you understand the idea of the stopping potential at the same time. So I will draw the photocell at different positions. Okay, so I'm going to start off with positive first. Okay, so when your V is positive, your photocell here, so I'm going to draw the photocell here to correspond with the positive V. Alright, so I have drawn now for us a bunch of photocells, and this one on the far right to correspond with a positive value means that this is positively charged. Okay, so here if it's positively charged, all the electrons that escape the metal surface, or it gets a bit of help, you know. So the electrons that escape the metal surface, they will have a different kinetic energy, right? Remember, just now I showed you in the simulation, some will travel very fast and go directly. Some will need a bit of encouragement. Okay, maybe it'll go like this, and then because this is positively charged, it will go this way. So essentially, if this is positively charged, right, I can assume all the electrons will be able to hit the positive anode and then complete the circuit. So you will get a reading here. Okay lah, let's say here. So I'm gonna draw this one here. Okay, and as long as it's positive, right, I will probably always get a reading. So this one is not a problem. Can be slightly positive, can be very positive. But what about 0? If this is 0 or maybe slightly negative. Okay, so anyway, just to label the voltmeter reading, voltmeter was connected across here. So here to here is your V, and V is positive. Okay, so now here there is no potential. V is 0. So if V is 0, this means that this current probably will begin to drop. Alright, so when I say begin to drop, right, it may not like have 0 all the way lah. Okay, sorry, deleted wrong stuff. It may not be you may not have reading here. So maybe this part here, it needs a slight positive, there only increase. So here it will begin to drop. Okay, so the reason for this slight drop here is because when this is 0 volt, some of the electrons, I mean, if let's say we're talking about the electron with high speed, of course it will reach, no problem. But if you're talking about some random electron with which is the direction a bit out one, it may not reach unless I put a parallel plate. Or let's say this electron that shoot out but then don't have enough kinetic energy, so it slowly moves its way here, or maybe it ends up overshooting like this. So not all electron can reach the anode because this is not positive. But this one it will, because even if the electron's trajectory is out, let's say it's supposed to move in a straight line like this, positively charged anode would deflect and pull the electron towards it. Alright, so I guess for this one I should write a note for you. Okay, so in this case, if the anode is positive V, all electrons are attracted to the anode, and they are able to arrive, and you get this maximum current. This maximum current here is, we call this the saturation current. But in CIE, we also can call this the rate of emission of photoelectron. Okay, so let's say now we want to make it negative. Okay, and if you're struggling to see this, let us look at this sim again. Okay, so if let's say in order to render this a bit better, I decrease this and I also bring up the frequency. Okay, so now you will see that at this intensity, you have electrons, some of them traveling at different speeds, some of them a bit slow. I guess eventually they will reach here. But if let's say you look at the shape of a photocell, not all will reach. Okay, and then I'm going to show you a graph of current versus battery voltage. All right, so right now the voltage is 0. You still have current, but if I make the voltage positive or slightly positive, you will notice that, let me zoom in so you can see. You get this saturation current. Okay, so this one is positively charged, all the electrons will arrive. Okay, and of course, if I make it more and more positive, the electron will arrive faster and faster lah. But it doesn't change the current because the number of electrons arriving per unit time is still the same. It's just that now they are traveling faster. But the number of electrons is still the same. Okay? So, as you can tell, look, you may be thinking, Miss, if we put like low one, wouldn't the current drop? Not really. As long as it's positive, the total number of electrons that hit this thing per unit time is the same. Remember? Okay. So you can see that when you make this more and more positive, the total number of electrons hitting it per unit time is still the same. The current is still the same. Okay. But what happens when we swap it to negative? Negative. Oh. Now something interesting happened. You can see the electrons begin to slow down, stop, and they get attracted to the negative terminal. To the positive terminal here. Hiyo, not enough energy. So let's say it is slightly negative here. Not very negative, but slightly negative. This current already begin to drop. Some of the electron can arrive, but not all. Some can arrive. Some, the very slow one, will travel out and then lose all the energy and fall back down. Some travel fast enough will arrive. Some too slow, lose energy and fall back down. It's a bit like jumping. You want to jump up potential gradient, but you don't have enough kinetic energy. So if I make this terminal more and more positive, and I make the opposing terminal more and more, you see this one almost reach liao, but then fall back down. So sad. Rip. Okay. So if I make this more and more negative, eventually the current will drop to 0. Even the most fast, the most energetic electron, also GG.com, cannot arrive. I want to reach, almost there, fall back down. I want to reach, almost there, fall back down. Hiya, this is a sadness. Almost there. Are you going to reach? Nope, fall back down. So this is what we call a stopping potential, because this negative potential has succeeded to slow down even the fastest electron. Okay, so what are the different things that you learn here? Number one, this shows that the electron has a range of kinetic energy, because as I increase the negative potential, if you check out the graph on top of my head, as I increase the negative potential, okay, less and less electron will arrive per unit time. So think of current as number of electrons arriving at the opposite plate per unit time. The number of electron release is only dependent on the photon. Right now, I'm not changing anything about the photon. I'm not changing the intensity. Okay, if I want to create more electron, I have to change the intensity, which I will talk about later. Okay, so right now, what you see is a phenomena where there's a range of kinetic energy. So when I make this battery more and more negative, or I make this plate more and more negative, it is less and less likely for the electrons to arrive at this plate. Harder and harder for the electron to arrive. until this one is so negative that this thing dropped to 0. So this is how we know, number one, there's a range of Ke. They're all at different speed, because all of them, you can see they hit different maximum height. And number two, there will be a large enough potential where I can stop everybody. That is the best. We can stop everybody. Okay, so I'm gonna write that down for you. Okay, so right now, if you want to think of the stopping potential, this is 0. Not all electrons arrive. I need to make it more and more negative. Okay, so here the current will begin to drop. As you see just now, drop. Eventually, it will hit 0. Where it hits 0, this is the point where we call stopping potential. Vs. So this will be negative. Stopping potential is when here the voltmeter reading is negative Vs. So if this is negative, right, what this means for the electron, for the most energetic one, I want to come here, almost bye-bye. For the least energetic one, I can, no, I can't. For the least energetic one, maybe I can, no, I can't. For this one, maybe nah. Sometimes the electron can even be like, I'm headed, nah, bye-bye. So the negative, this negatively charged anode, kind of like stops all the electrons from arriving. So this is Vs. Okay, so right now, even if let's say I change this to slightly negative, or negative V, but this is less than Vs. Okay, this also means that what will happen now is some of the electron will have enough energy and can reach. Some of the electrons will go up. I'm almost, nah. Some of the electrons is like, maybe I can, not really, no. Okay, so the whole idea here is the electron's kinetic energy at this point here, all electrons are attracted to anode, and no energy is required after exiting or after emitted from metal surface. So because of this, here you can say this is called the maximum rate of emission. Of photoelectron, also known as current lah, okay? What about the middle case? Let's say the anode is negative V, but less than Vs. Negative V, but less negative than Vs, which is a bigger value than Vs. Yeah. Less magnitude. Let's not fry our brain. Than Vs. Okay, so this is negative V, but less magnitude than Vs. So magnitude. So what will happen is some of the electron from deeper inside the metal will not have enough or sufficient kinetic energy to arrive at the anode. Okay, because don't forget, if you think about the drawing here that you have seen before, hopefully, this electron all come from different one. So if you're talking about an electron deep here, this one need more energy because it goes like they only come out. Okay, whereas if you're talking about this electron, this one here, be like, I'm so close to the metal surface, I can come out with a lot of kinetic energy. So this black color electron needs to enough energy to travel out to the metal surface, leaving it less kinetic energy. So if let's say now I make it even harder, I set up a negative anode here. So this anode is negative V, then it's even harder for this one to go here. Even if I do a parallel plate, it's just harder because look, if I make this one negative, or if I put a parallel plate lah, because I already draw this direction. This one is like, you know what, guys, I don't have enough energy. I'm too tired. I use all my energy to come up on the metal surface. Okay, thanks, bye. Because it's being pushed away. All right. So whereas this one may have enough energy. So that's why there's not all electron can arrive at the metal surface. And then this one also shows, so hence this shows that the photoelectron has a range of Ke, of kinetic energy, because the ammeter reading I decreases gradually when V is negative. Okay, so this I decreases gradually when V is negative is this part of your graph here. This part. This part. Okay, your saturation current is this part. Nah. Okay, maximum rate of photo emission or current. Okay, so this is the important part here, which is the idea of stopping potential. Okay, so for stopping potential, you can stop. So now your anode is negative Vs. So stopping potential is defined as the potential, or rather I prefer the word negative. We start early. The negative potential difference across the photocell that is able to stop the most energetic photoelectron. So the photoelectron will lose all of its kinetic energy. Okay, so right now, if it loses all its kinetic energy, the change in kinetic energy, or rather the most energetic photoelectron, if it's most energetic photoelectron, so this one is related to Ke max. So this Ke max will be equal to work done by the electric field to slow down the electron. Work done by E field. So we're going to assume that the potential setup is a uniform electric field, so that our brain is not that fried. We set up a uniform field. So here your Ke max is equal to E, because we are still accelerating an electron, Vs. Because work done, remember from your chapter 17, work done by charge is QV, or Q delta V. Okay, so the delta V will be the potential difference between these two plates here, which will be Vs. Okay, and Q here will be the charge of the electron. So I'm just going to write EVS lah. Okay, of course this Ke max you can write half mv square, but and the m here will be the mass of the electron, but I will not write that down, because I think at this point in time Ke is half mv square should be at your fingertips lah. Okay, so I'm just gonna highlight this one. Okay, so this stopping potential, this is the definition of stopping potential here. Right here, stopping potential. This is the definition. Okay, Vs, which is the negative potential difference across the photocell to stop the most energetic photoelectron. So we can stop the most hyper one, also stop already. So that's why this graph will drop to 0. And after that, it will stay at 0 forever and ever until my pen change color. Okay, looks like it's not going to change, but it's going to stay at 0 lah. So if you were to look at the simulation here, let me bloop it up for you. If I make this more and more negative, this one will stay 0. Nothing will change the stopping potential. Okay, but in this, so this Vs, you can see how the current will flow. If I put positive, all the electron will arrive, but the amount of electron that arrive per unit time is the same. You see, how do you know? Look at this current. 12.6. Let's say I make it to positive 2. So it's still 0.126. I make it to positive 0.6, still 0.126. So this saturation current will not change until I put it to 0, or even better, negative. Then some will reach and some will not have enough energy, like this one, and crash back down to the positive cathode. I am sorry, bro. Okay? But if I make it negative enough, then even the most energetic one, also gg.com, cannot arrive there. 0. I think it's negative 1.4. But yeah, you can play around with this sim and find the stopping potential. See, almost, but not reach. Okay? So what are the main ideas that you learn in this video? Number 1, you learn the setup, okay? And how to install the ammeter to measure the saturation current. Number 2, you define for ourselves the definition of threshold frequency. So you have already done this part of the observation. Instantaneous emission, there's a threshold frequency. Okay, and number 3, you understood what was the stopping potential, and also this graph. So if I make this plate negative, more and more negative, less and less electron will arrive. So that is what we have learned in this video. In the next video, I want you to think about what will change the graph. What would change the value of this saturation current, and what will change the stopping potential. Okay, so that will be in the next video, because this video is being a bit too long. All right, I will see you in the next one. Bye bye.